Imagine a robot delicately picking up a fragile object or feeling its way through a cluttered environment. How does it know not to crush something, or how much resistance it is encountering? This incredible ability comes from a specialized component that gives robots a sense of touch and weight. A force sensor, also known as a force transducer or load cell, measures the mechanical force applied to it. This force can be a push, a pull, a twist, or even the weight of an object. Essentially, it quantifies the interaction between the sensor and its surroundings, converting physical force into an electrical signal that a robot or control system can understand and react to. The core mechanism behind most force sensors involves a physical deformation that is then electrically measured. For instance, many use strain gauges, which are tiny electrical conductors bonded to a flexible material. When force is applied, this material deforms, causing the strain gauge to stretch or compress. This change in shape alters its electrical resistance, which is then precisely measured. Think of it like a very sensitive spring that changes its electrical properties as it's squished or pulled. The magnitude of this resistance change is directly proportional to the applied force, allowing for very accurate measurements. To accurately interpret these measurements, force sensors often incorporate a Wheatstone bridge circuit. This electrical circuit is designed to detect very small changes in resistance, making it ideal for converting the subtle deformations of strain gauges into a robust, readable voltage signal. Calibration is a critical step, where known forces are applied to the sensor, and the corresponding electrical outputs are recorded. This process establishes a precise relationship between the electrical signal and the actual force, ensuring the sensor provides reliable data within its operating range. There are various types, such as single-axis sensors measuring force along one direction, and multi-axis force torque sensors capable of measuring forces and torques in up to 6 dimensions. For engineers and roboticists, understanding force sensor data means unlocking new levels of robotic capability. Consider a surgical robot that needs to apply just the right amount of pressure during an operation to avoid damaging tissue, or an industrial robot precisely polishing a surface where consistent contact force is paramount for a uniform finish. These sensors enable compliant motion control, allowing robots to adapt their movements based on physical interaction rather than just following a pre-programmed path. This is a game changer for tasks requiring dexterity and human-like interaction. Ultimately, force sensors empower robots to move beyond simple, rigid actions and engage with the world in a more intelligent and adaptable way. By providing real-time feedback on physical interactions, they are fundamental for creating robots that can perform complex manipulation tasks, safely interact with humans, and operate effectively in dynamic and structured environments. This ability to sense and respond to force is a cornerstone for the next generation of truly collaborative and versatile robotic systems.
If you love robotics, like, subscribe, and keep building with us.